In this video, I will explain you the concept of self-inductance. Now we will see the definition first. This is a phenomena of flux made by a coil linking to the same coil itself. Now the illustration goes in this way. Current is going through a coil, and when current is going, current will create a magnetic flux, magnetic field basically. So this field lines that will link with the same coil. Now that is a flux linkage, right? See, current in the coil that produces a field around it, and the same field will be linking with the same coil. So who has created it? The same coil. And the flux linkage is happening to which coil? To the same coil. So that is the name suggests self-inductance. Okay. So the self has induced an EMF. Okay. Now we will see the value of self-inductance. As per the law, that it has defined that the flux linkage with the same coil is directly proportional to current passing through it. It's very obvious, right? See, when a current is passing through it, if it is a smaller current, then the magnetic field around that will be less. Okay, so when field is less, magnetic flux also will be less, because flux is equal to B into A into cos theta. So when B is less, flux is also less. Now higher the current, higher will be the intensity of magnetic field around it, flux will also be more. So this is the definition. Flux is directly proportional to current passing through it. Flux linking with the same coil, okay. Flux linking with the same coil is directly proportional to current passing through the same coil. Now this proportionality has converted to an equation, that is, this constant of proportionality is self-inductance into I. Now higher the self-inductance, higher will be the flux linkage. Lower the self-inductance, lower will be the flux linkage. Now we will see what are the different parameters that L dependent on. Okay, now, so we have got an equation for flux here, and we already know an equation for flux, that is flux is equal to B A cos theta. Now here area is in this way, magnetic field line is in this way, so angle is 0. So cos 0 is 1, so this will be just BA. Now magnetic field created by solenoid, we already know what is that value, mu 0 Ni. This is the value, mu 0 Ni. But this N is small n, that represent capital N by L. So capital N is the total number of turns, L is the length. For example, N, if it is 100 and L is 10 meters, then turn density is equal to 100 divided by 10 meters per second. Sorry, 10 number of turns per meter. Okay, turns per meter, or turn has no unit, that is per meter unit. So magnetic field I have substituted here, and area, what is the area of coil here? Pi into radius of, so it's a circular section, right? So pi into r square will be the area of cross section. And one more thing, so this will be the flux linked with one coil. So field lines are there, these field lines are linked with each and every coil, that makes a solenoid. So with n number of turns, so this is with one turn. Now with n turn, so this n is capital N, total number of turns. It's not small n. With n turns, flux linked is equal to this value into n. So capital N into mu 0 Ni pi r square. Now this capital N can be written as small n into L, because we already have small n here, right? So we will bring all the equation in terms of small n. So capital N is equal to small n into L into mu 0 into small n again, then I into pi r square. So we got an equation for flux here. This is the equation. So this is the final equation. Both of this equation can be used. Now here we will substitute, we will equate both the equations. This is as per the law of self-inductance. This is the one which we have learned for magnetic flux. So we will equate both. L into I is equal to this value, which is, this one is mu 0 and n into n square, mu 0 n square I have considered, then L into I into pi r square is nothing but area. So I can keep it as pi r square or area, I will make it A. Now this I and this I is the same, right? Now here the I is nothing but current passing through the solenoid, and as per this equation also it is current going through the circuit. Both are the same, so I can cancel these two I. So what is the equation for self-inductance? L is equal to mu 0 n square A L. A very important equation. So this A can be considered as pi r square here, and substitute here you will get. So depending on what are the value given, you can use the equation. Now instead of small n, if capital N is given, now you can change the small n into capital N. What will be the equation? Self-inductance is equal to mu 0, small n is equal to capital N divided by L. So its square will be n square by L square AL. Out of that 1L and 1L will cancel. So the equation will become mu 0 into capital N square A divided by L. So this can be another equation. So depending on the parameters given, you can use. So generally I have learned mu 0 n square AL because that is all the parameters are in the numerator. Okay. So we got two different equations for mutual inductance. Sorry, self-inductance, which is mu 0 n square AL, where n is in small letter, that is turn density, and another equation is mu 0 capital N square AL. Now if someone is asking that when we are elongating the coil without changing its area of cross section, what will happen to self-inductance? See, when we are elongating the coil, number of turns remains the same. So when the turn is initially in this way, when we are elongating, this will become in this way, but the turn will be the same. Okay, so when we are seeing the variation of one parameter with another, then that two parameter should be the only one which is varying. Others, everything should be constant. So can I use this equation? No, because see here in this equation, when I am increasing the length, L is changing, but turn density will also change. Because see, previously in 1 meter, see in 5 centimeter 4 turns was there. Now when I am elongating, in 5 centimeter only 2 turn is there. So this one is changing, this one is changing, and this one is changing. So I can't use that equation. I have to use this equation. L is equal to mu 0 n square AL. Now when I am increasing the turns, n remains same, increasing the length, then total number of turns remains same, area remains same, mu 0 remains same. What is changing? Total length is increasing, L will decrease. So L will decrease on elongation, Now at the same time, when I am adding one more coil to this, having the same turn density, in that case also total length is increasing, right? But the turn density hasn't changed here. It's the same coil, I have added one more. So what will happen to the inductance? In that case, I will use this equation because turn density is the same thing. Area is the same. I have added one more coil having the same area. Now mu 0 is the same. So I can say that in that case length will increase. Others everything will be the same. So L will also increase. So which equation I'll use? Mu 0 n square AL. All others are same. So L increases on. This is also elongation. I can say that elongation with delta n is equal to 0. Delta n means change in turn density is equal to 0. But here in this case, delta capital N is equal to 0. What is that? Total number of turns is not changing. But here it is changing. Now, we have got the equation for self-inductance. Next thing is how to get the self-induced EMF. That is, induced EMF is equal to minus d phi by dt. Now we have learned in the first thing when I have introduced self-inductance, in the flux linked is equal to L into I, self-inductance into current. So this is equal to minus d by dt of L into I. And L I can take outside, so minus L into di by dt. So there will be induced EMF. This is very important. There will be an induced EMF only when the current is changing in the circuit. Whenever the current is changing, then magnetic field will change, and that will change the total flux linked with the same coil. Okay, now whenever there is a change in current, that will create a induced EMF. But if there is no change in current, there won't be any induced EMF. Let's say current I is passing through the circuit at constant rate. Will there be an induced EMF? No, because as per the equation, di by dt can only make an induced EMF. So this is termed as back EMF, because the reason is self-inductance, and this EMF will always try to oppose the external EMF. See, when we are sending a current in this direction, let's say this is positive and this is negative. Now current is increasing in this direction. Now it has to decrease the flow of current as per Lenz's law. It will oppose the cause that producing it. The cause is increase in current in this direction. So what this will do? This will create an induced EMF that will oppose the change. So this will behave as positive and negative in this way, and will try to send current in this direction. So when current is increasing in this way, this will try to send a current in this way by creating a potential difference in this way, so that this change is opposed. So this EMF is termed as back EMF. So E back EMF is equal to minus L di by dt. Now this is a very important equation, that using this thing we can define what is self-inductance. Say for example, we have made the current to flow in a circuit in such a way that at every second change in current is 1 ampere. So that is 1 ampere, then 2 ampere, then 3 ampere, 4 ampere, 5 ampere. So 1 to 2 1 second, 2 to 3 1 second, 3 to 4 1 second, 4 to 5 1 second. So the change, what is the change here? di is equal to 2 minus 1 divided by dt 1. So di by dt is equal to 1. That is, change in current in every 1 second is equal to 1 itself, 1 amperes. Now in that case, when this become 1, then back EMF is equal to self-inductance. Easy, no? So we are making a coil and we are sending current in such a way that in every 1 second change is 1 ampere. So 1 to 2, 2 to 3, 3 to 4, that change will happen in 1 second. Now in that circuit, if you are measuring that induced EMF, back EMF, that will be is equal to self-inductance. See, keep this as 1, then E back EMF is equal to L itself. Minus you can neglect, that means it is back EMF. The moment I say back means I can ignore this. So this is a very important derivation. Okay, thank you.